So today I'm going to talk to you about molecular problems. I'm a quantum chemist. I'm interested in studying molecules, and I want to talk to you about how we can make models of electrons in molecules. So just give you some background and motivation. So we're interested in molecular systems, but sometimes we're interested in molecules in complex environments or in surfaces, like here. For example, I might want to study a reaction that happens on a surface. I have an organic molecule, and you can convert it from one form to another. This problem involves near-degenerate states and the interaction with the surface, so I need to reduce it to something manageable. Here's another one that we're working on right now. Maybe I'll show you something towards the end. This is an experiment that probed basically the isomerization of a molecule on the surface, and it's a quantum-to-quantum resolve experiment. So we want to get the vibrational quantum level of this molecule in both configurations. And so to do that, we need an accurate potential. And we need the potential even when you stretch this bond and basically go in a regime where strong correlation develops. So one way to create models is to decouple degrees of freedom. So, and from my perspective, we have a problem where I have many one-particle states. These are orbitals, and we want to separate them in groups. Some are treated at a high level of accuracy, and the other ones, supposedly many of them, are treated at a low level of theory. And that's going to make our calculation affordable. So, for example, in this example that I mentioned before, what degrees of freedom I can separate. So I want to, for example, treat at eye level the static correlation that develops in the molecule when I stretch this bond. I also have to account for the molecule surface interaction, and preferably quantum mechanically. But then when I'm far apart, then I can model the remaining electrostatic interactions with, say, classical charges. All right, so the technique I'm going to talk to you about today is, I think, a very natural way to do model reduction, and is to use similarity transformations. So specifically, this partitioning and decoupling of degrees of freedom is going to happen in the form of a transformation of the Hamiltonian. This is a similarity transformation. I'm going to talk about this in a general form, and then I'm going to specialize to specific type of transformations. But they're very useful, and they're used quite a lot in quantum chemistry, because I can, with this transformation, say, extract an eigenstate. We use this technique a lot when we want to do high accuracy quantum chemistry. Or we can decouple a subspace out of this large space of many body states that we deal with. And then the little block in the matrix represents our model, reduced dimensionality problem. So now I want to give you show you how this is pervasive in the field. So I emphasize the point of view where you transform the Hamiltonian, but there's an entire set of techniques that kind of emphasize the other perspective, where you apply this transformation to a state, and that preeminently couple cluster theory and equation of motion couple cluster methods stem out of this approach. And then more recently, the multi-reference generalization are all based on this approach. Here, this S operator is a couple cluster or an excitation operator, so it promotes electrons from whole to particle states. Another way to parameterize this transformation is to use a unitary operator. So A is anti-emission, and the exponential of A then becomes unitary. And this has a very long history, so starting with Van Vleck and the Schrieffer-Wolff transformation. Quantum chemistry is known as unitary couple cluster theory, which is now making a reemergence because it has connections to quantum computing. And there are also methods that generalize these techniques to the multi-reference case. So I'm going to actually be focusing on this last quadrant of the slide. But I'm going to try to carry the discussion from a point of view like how we create models. So what are the challenges? So the technique is so trivial that we might ask, well, why is it so difficult? Why don't we do it? So I'm going to talk to you about three problems that one has to deal with. And all modern formulation of this formalisms that I'm talking about basically combine these, have to solve these three problems. The first one is taming the cost of the induced interactions that you get when you do this transformation. So let me explain that in a second. So we start, so the quantum chemistry Hamiltonian is a general operator that has up to 2-body interactions without any restriction except that maybe this operator commutes with the spin operator, so you have certain restrictions here. But it takes n4 matrix elements, where n is roughly the system size. You could think of n being the size of the basis that we're using. Now, what happens when we perform a similarity transformation? If I look at the operator once it's transformed, I can write it again as a sum of second quantized operators. And I'm going to open a little parenthesis because I appreciated the fact that people have explained their notation, and I just realized that I've introduced a notation without explaining it. So when you see an operator like this with 4 indices, that really is a quadruplet of operators, 2 creating electron and spin orbitals p and q, and 2 annihilating operators in RS. So instead of writing every time 4 operators, I'm going to write these compact notation.
It's normal order, is that assumed?
Not yet. So here we have 1-body operators, 2-body operators, and then we start to get these induced 3-body operators that diagrammatically you can represent in this way. And this expansion doesn't terminate at 3, it continues. And here, of course, what's the issue is that already storing these matrix elements, the cost goes to n to the 6th, but now computing this matrix element has typically a cost that is higher to n to the 6th, so n to the 8th, n to the 9th. And so that's why I'm talking about taming the cost. So we have to deal with this increase in complexity. So this is a form of conservation of misery. So either you solve this problem in a very large space, or you reduce it to a small space, but you deal with a more complicated Hamiltonian. But now, if, of course, the degrees of freedom that we are decoupling are not too relevant, there's going to be a way we can deal with these interactions. Okay, so that's problem number 1.
So I have a question. You said you went to a smaller space. So what? So the 3 indices quantities are much smaller.
Yes, they're going to be in whatever space defined by model. Yeah. So
It could be only 4 by 4 by 4.
It could be 4 by 4 by 4. Yes. But it also means we have to develop the technology to deal with the 3-body interactions, which is not impossible, but it could be done. Another big problem that I'm not going to address, but I need to introduce because at some point we're going to have to define what a model is for us, is to come up with a good 0th order model. So this is actually an interesting aspect of creating models, is that you can't create models. I mean, a good model already includes some ideas of what the solution is. Yeah. So the way I'm going to think about this is that I have some eigenstate that I want to represent, and this lives in the full Hilbert space. And I separate that space into a low dimensionality space, small, called the model space, and the eigenstate projected on this subspace is going to be my starting point for creating the model. So I'm going to try to create a model that works around this reference state. And this eigenstate shouldn't be too far away, because otherwise everything is not going to work well. So in essence, this is what chemists call multi-reference theories, because here we have a linear combination of many body states determines this reference state. And it might be that I have to do this self-consistently because, of course, I don't know what's the exact eigenstate. But I'm going to neglect that point from my talk. So one way to do this is to now go to the many-body basis of determinants and say, well, let's say I want to describe the low-energy physics. So I might pick P, this model space, to be the low-lying determinants. And then the high-lying determinants are going to be living in Q. And I'm going to eliminate these and create a model that lives in this space. Now, one of the issues that's going to play an important role in my talk is this one. So let's do a perturbative analysis, and let's look at this third problem that's called the intruder state problem. So now what I can do, I'm going to do kind of simplest thing I can do. I'm going to represent the Hamiltonian in a basis of determinants. I'm going to consider these blocks, or maybe even the diagonal part of this block, at zeroth order, and I have this part and the coupling V. I'm going to treat V as a perturbation to first order. Now I can apply my Bolshevik transformation here. I get this expansion, and one of the simplest thing I can do is I can try to remove the coupling to first order. And the degree of freedom I have is the operator S. So I can ask that this commutator H0 plus commuting with S cancels lambda V. And if you do this, you get one of kind of the simplest ways to create an effective Hamiltonian. So an Hamiltonian that lives only in this little block P by P, where you have the original Hamiltonian plus this second order correction where you get a coupling squared and a sum of denominators. And of course, you can imagine that this is going to be a problem because we can get the small denominator problem. So what that implies is that if I don't choose my model space carefully, these differences could be small or even zero. So what is the sad truth? Is that for chemists, this plagues a lot of our problems. And I've never generated credible data for it. But for this talk, I decided, well, let me try to do a very simple example and show what it looks like. So here's a simple reaction. You take beryllium hydride and you remove it, remove the beryllium atom, and you end up with beryllium plus H2. X is going to be the coordinate that controls this transformation. And I'm constraining the path. Okay, so I'm doing some simplification here. In this problem, something interesting happens. At X equals 0, so when you have this molecule, you get of course, we have 6 electrons. I'm not showing the core electron, but the 4 valence electron populate these orbitals that look like that. At X equals 4, if you look at the R2 Fock determinant, it looks like this. So of course, we have dissociated the molecule. Beryllium is here, hydrogen is here, and you get orbitals that connect to each other.
X equals 4 is all the way over?
Yeah, the distance from the center of mass and the beryllium is 4 Bohr. So it's roughly 2 angstrom. Okay. And notice what happened. This orbital that has this kind of anti-symmetric with respect to a certain plane of symmetry is no longer occupied in the R2 Fock determinant, and this orbital here is occupied. Now this is a 2s orbital of beryllium. And so that's the ground state configuration of beryllium is 1s squared, 2s squared. So we would expect that. So now this is problematic because it tells us we can't include one of these two configurations alone. We have to include both of them, both determinants. However, then you go and do this analysis where you take the basis of determinants. So these are many body states. And I compute the expectation value of the Hamiltonian. So I'm going to call this the energy of a determinant. But this is not the energy of an eigenstate. It's just the diagonal of that matrix. And you see something interesting happens. If I am here at X equals 0, there's a huge gap between my lowest determinant and all the other determinants. If I'm on this other side, there's a sizable gap between this determinant here, represented by the red line, and the other determinants. Now, these two determinants cross. That's why I need two determinants to represent this reaction. But what's more problematic is that now we get all these other states that could interact with the second determinant or the first determinant. And so if I look at the opportunity to get zero denominators, they abound. So this becomes a pathological problem. So the issue is not, so if we put ourselves in a single configuration, this problem is not that problematic. But if you want to change the parameters in your calculation, you have to worry about this. So what are we going to do about it? Well, there's not a lot of good solutions right now, or at least, and today I'm going to talk to you about one of them. But certainly, we can't play a game where we make the space bigger and bigger, because this problem kind of multiplies. Because suppose I say, well, let me take this other state and add it to my model, because that's going to help me avoid that small denominator there. Well, of course, then this state is going to cross other states, and that leads to a cascade of crossings that. And so that's not physical, because, for example, if you're describing the ground state, of course, this second, if we are here and we're describing the ground state is going to be mostly this determinant, and this second determinant is not going to matter. All right. This problem, of course, is well known. It shows up in perturbation theory. This is a simple calculation of a molecule showing these divergences in perturbation theory that appear at certain points. This shows in non-perturbative methods. And it shows, of course, naturally in perturbation theory. So here's, for example, you compute a curve for a molecule, and if you apply no denominator shift in your perturbation theory, you at some point get this divergence. All right. So now in perturbation theory, you can play this game of level shifting, and that it's okay. But we really don't have a technique that applies to non-perturbative theories. Okay, so we have to come up with a way to solve this problem, or ameliorate it, at least. So today I'm going to talk to you about this technique they developed a couple years ago. It's called the driven similarity renormalization group. So let's talk about the general issue of removing singularities from equations. And I'm going to just bring up a very simple toy problem. And I want to show you that this is not a super trivial problem. So let's take the linear equation f of x, and let's find the zero. And of course, I can write the solution down here. Now, this is the type of equation that we solve in perturbation theory. And the singularities, as we see, appear when a equals to 0, or can cross a 0. So the typical approach of level shifting does this. It shifts a to a plus omega, where omega is a parameter. And so now I get a regularized solution. So this solution is going to work when a equals 0. But unfortunately, this is not a general solution, because I just move the singularities. I'm not really getting rid of them. Another approach that we could consider is regularization. So we could do L2 regularization, where we penalize solutions that have large value of x here. And now our regularization parameter appears here. Now, if you do it in the linear case, you get a solution like this. And this is one way, this is a sensible way to remove, at least in this linear equation, this issue. But if we try to do this for a more general type of problem, like here, then we have this kind of more complicated equation that we have to solve, where we have this function we're evaluating and its derivative. They're multiplied. And from the point of view of many-body theories, this is not a good idea. First of all, these two terms are disconnected. So we're going to break some properties there, like size extensivity. And it's going to be much more difficult to evaluate quantities like this. Nobody, as far as I know, has tried regularization like this to solve the problem that I mentioned, but I want to mention it as because this analysis, I think, shows it's not particularly promising. So what are we going to do? So as the title implied, we're going to use a formal renormalization group. And in particular, we're going to use a technique called the similarity renormalization group, which was developed in the mid-90s, so by Wegner and Klocek and Wilson. So these were techniques that were similar, introduced in different contexts. So I'm going to mostly refer to the techniques used by Wegner, who worked in condensed phase, solid state physics. So what is the premise? So let's start with our Hamiltonian. And here I'm representing the Hamiltonian as a matrix, but of course this is just a cartoon to represent the full many-body operator that I'm describing. And now if we look at the spectrum of denominators, so potential energy differences between the diagonals of this, there's going to be a range. So this range is finite for the problems that we're dealing with. And it's going to stop at some lambda value. And the idea is to do a series of unitary transformations where what we start to do is eliminate the degrees of freedom where this lambda is very large. So here we can think about, this is kind of the analogous of perturbation theory, where we eliminate not the degrees of freedom that have small couplings, but the degrees of freedom that correspond to large denominators. So that's a very well-controlled form of way formulating perturbation theory. And here I'm showing a discrete transformation that's going to be more general. And I keep doing this until I reduce the spectrum. And as I do this, if I ordered my basis according to the energy of these determinants, I'm going to get kind of a banded matrix with approximate zeros that develop at these two corners. And if I do this transformation, the small denominators that cause this intruder state problem are never going to be dealt with by this unitary because they correspond to 0 or small denominators. So this is the technique I'm going to use to avoid the small denominators. Okay, that's the condition that defines the band. All right, so now in the context of many-body theory, the way you do this is you map the Hamiltonian to this unitarily transformed Hamiltonian, and we introduce a continuum parameter S. So S goes from 0 to infinity. That's the intruder. All right, now we're going to identify a diagonal and undiagonal part of this matrix. These can be actually defined arbitrarily. They're operators that you define to remove. Is it me this time? Okay. All right. It was on mute. All right, so we have defined the good part and the bad part of the matrix that we want to eliminate. And we have this parameter that is going to go from 0 to infinity. And well, the condition we want to impose is that from 0, we have the original matrix. And when S goes to infinity, this quantity disappears. So if you do this numerically, this is what it looks like. So here I have a matrix, but this matrix represents entries in a tensor that correspond to an operator. And these different blocks are partitioning of orbitals. So in particular, I'm, say, decoupling some sets of orbitals coupled to other sets of orbitals. I'll define that later. And as you do this transformation, what you can see, you start to see this bandedness, but it happens in the context of these blocks. So here's, for example, at, say, S equal 0.5, I get this residual interactions, and most of the other ones are 0. And by, if I go to a sufficiently large S, I just have a few residual couplings here, and these correspond to the small denominators. These are the bad guys. Now, what can I say? So, so this is the thing I said before. But what's important here is that I can relate this parameter S to an energy cutoff. So, and that's the relationship. It's 1 over the square root of S. And the way you see this is by basically taking this similarity formalism, do a perturbative analysis, and you can show that this happens. And we kind of assume that this happens also when we go beyond the perturbative regime, but there's no good reason to believe so. Okay, so so I have to point out that a couple of things, though, is that these sets of techniques were tried by other people before. In particular, I want to point out to some work by C. White in early 2000. And really, this was embraced by the nuclear physics community in the 2010s. So they applied it in many different ways, especially the work of Scott Borkner and Heiko Hargard is relevant in this context. So this is a differential formalism. And what I want to talk to you about is how can we realize this without solving an ordinary differential equation. I'll mention the ODE in a second. So if you now take the equation I've shown before and you cast it in terms of a differential equation, I'm going to have to skip a lot of details. But in the end, in the SRG, this is the problem you solve. You have a differential equation for your operator, H, and expressed as a double commutator. So this kind of technique is already known in matrix theory as the double bracket flow equation. And what's important is that the diagonal part of the Hamiltonian appears as one of the components of this double commutator. And you can show that with this choice so you can set up different differential equations, but with this choice of what is called the generator, you can see that this flow satisfies this condition. So the derivative of the trace of the non-diagonal part squared is negative, meaning that if you solve this differential equation, you will tend to decrease the magnitude of these off-diagonal couplings. So what it looks like is you start from an operator, you flow, and this goes for s equal infinity to a operator without the off-diagonal part. That's the part that I'm setting to 0. Sorry?
Colors are reversed, it seems.
Yep. So what we propose to do is the following, is to treat this as a finite transformation. So we can express that as a similarity transformation. But now we're going to parameterize the operator that is exponentiated. And so we do not need to, we're going to generate the transform Hamiltonian. And our goal is to still get from this full operator to the pure diagonal operator. But we don't want to do it by solving the differential equation. What the intuition is this, is that it doesn't matter here the path that we take. We know we want to get to this diagonal form, except that we want to avoid removing the terms that are dangerous because it can lead to the interior state problem. So how do we bridge these two theories? So we decided to do the following, is to try to find the transformation A, or find an equation in A as to satisfy, in such a way that this transform Hamiltonian mimics this other transform Hamiltonian. And of course, again, it's not important they do follow the same path, but they tend to the same limit. So therefore, we can do this matching using perturbation theory. And we end up rewriting this equation in this form, where I have the transform Hamiltonian, I have this non-diagonal part, and I set this quantity equal to an operator that we call the source operator. And you can imagine that if I had this operator from the SRG, I would just be able to set the source operator to this operator. Of course, I don't know this transformed operator, so I'm going to define a new operator as R. So we find R by matching these two theories at low-order perturbation theories, like first-order perturbation theory.
I'm sorry, I'm a bit confused.
Yes.
Which, the R of S, to which operator in the upper part of the slide does it correspond?
Yeah, so R does not enter in the SRG. It's something that, so this is the equation that we're postulating. And we're saying, by solving an equation like this, we can reproduce a path that is similar to that of this SRG. So I'm writing, so this now becomes an implicit equation for A. That, yeah. So I'm going to start with, maybe if I explain this point. So at the beginning, when S equals to 0, I want this side actually to be equivalent to the Hamiltonian, to the starting Hamiltonian. So that, because at the beginning I've done no transformation. And when I go to S equals infinity, this side should be mostly 0. So now this equation is nonlinear and it's implicit because I'm solving for A given this condition. So now, how do we realize this in practice? So first of all, to define this to define the model state, the model space, we're going to use a linear combination of determinants. And how do we pick the determinants? This is kind of an established way in quantum chemistry, is where you basically partition the orbital space into groups of orbitals. They're called core, active, and virtual, but they just reflect basically a choice of occupation. Core orbitals are kept doubly occupied in this model. Active are partially occupied, and empty are empty. And then we generate all determinants that satisfy these constraints. So for example, if I consider a model space where I have 2 electrons in the active orbital, in 2 active orbitals, then I can generate 4 determinants where I have these 4 arrangements of the active electrons, and the core electrons are all doubly occupied and are not shown. So in this case, I generated 4x4 effective Hamiltonian. So that's point number 1. The second one is the normal ordering, and this is an important aspect because here we use a technique that it's not very well known. It's developed by Debashish Mukherjee and Werner Kutzenig, and it's called it's a generalization of the concept of normal ordering for general Fermi vacua. So what Mukherjee and Kutzenig did is they define a way to express normal ordering operators, not as proper ordering of operators, but by defining a normal order operator in such a way that its expectation value is equal to 0. No matter what the reference state, there it is. So here the state could be, say, artifact determinant, could be like in my case, a general correlated state. It's a very flexible formalism. Yeah. And now the information about the state enters through the reduced density matrices of the zeroth order state. So these quantities are going to play an important role in the formalism I set up. But I'm going to gloss on these aspects. So when I introduce this form of normal ordering, I can express the transform Hamiltonian in a normal ordered form. And now those are normal ordered. So what happens when you do this form of normal ordering? For example, a single substitution operator is equal to a bare substitution operator minus the expectation value, so that when you take the expectation value of this side, it's equal to 0, and that's where I get my one particle density matrix of my general state. Now, when you go to higher order operators, you'll start to get higher order density matrices. So now this component, the form of normal ordering operators, basically, this is a cartoon to represent it. It expresses an operator as its vacuum expectation plus the fluctuation, which is the normal ordered part. So why is this useful? Is because when we now express this similarity transformation, say we are computing a term like this, where we have the commutator of two body operators. Of course, the only terms that survive has to involve a contraction between the indices. So I got the 3-body term. So this is a bare 3-body interaction, and this is expensive. But when I rewrite this in normal order form, this is a form of recycling higher order interactions. It shows up as a contracted tensor where 2 of the indices, say, are contracted with the density matrix or accumulant. So I'm hiding some of the technicalities. And this becomes an effective 2-electron interaction that captures some of the 3-body effects. So this is an important way to reorder our equations so that we get these effective higher order terms come back at lower order in theory. And then the type of diagonalization I'm going to do is it's a Fock-space diagonalization. So I am not going to project my equation in a subspace of determinants. I'm going to just manipulate these type of expressions.
Can I ask a question?
Yes.
What do you do when you have the quartic terms, say, with the 4 creation operators?
There's that also can be reduced down to a 2-body normal ordered, 3-body normal ordered, and so on and so on. Yes, it's more complicated, and because at some point when we have nested commutators, we don't evaluate the full commutator and then normal order it. We do it in a kind of systematic way.
So when you say that you reduce the truncation error of the DCH formula, is that like reducing this in the diagrammatic sense, or reducing this literally by the operator?
Yeah, so because if I introduce an approximation where I don't have 3-body operators, if I throw all this term, so if I don't work in this normal ordered formalism, I'm throwing away a lot of vital information. Instead, if I work in the normal ordered representation, this gets, I keep a term like this in my similarity transform Hamiltonian.
It's really in the diagrammatic sense, not necessarily in the literally operator.
Yeah, so it helps when I introduce diagrammatic approximations. Yep. And so I said I was here talking about how I work in Fock space, and so the part that I'm going to eliminate is actually just parts of these operators. And I'm going to define this as the part that lifts this reference out of this model space. And that's equivalent to this idea that I want to decouple these two spaces. So what does this look like in practice? So here I have my space, and I'm basically going to create an effective Hamiltonian that lives only in the space of active orbitals. Here are 3 components of the operators that perform a electron substitution. So this one moves an electron from here to here, this one from here to here, and so on and so on. And here's another one that just shuffles electrons around in the active space. Well, these 3 types of excitations will promote a determinant in the p space outside of it. And so these are the parts that I want to eliminate. And this one is fine. So how do I write my equations? I take the components that I want to eliminate. I have a operator equation. So I have one side of the equation. On the other side, I have this source operator. If I didn't do this formalism that I'm talking about, if I didn't do the renormalization, there would just be a 0 here, and I would just be trying to set these tensors equal to 0. But now I have this term here, and that gives me, when I equate the operator on this side with that side, I get an equation that looks like this, where I have a matrix element of this tensor. Now, I didn't go into details of how we get this, operator R, but I'm here showing you what it looks like. It has it's a bit complicated. It depends on the amplitudes that parameterize the operator A. And it has this Gaussian regularization factor, which is actually what you would expect from solving that double commutator equation. So that double commutator equation gives you this kind of diffusion. It's kind of a diffusion equation and gives you this Gaussian factors. So these are going to be important because they're going to suppress terms when I have small denominators. So when I have a 0 denominator, basically I get an equation that has a trivial solution, t equals to 0. All right, and then how do I parameterize my operators? These are second quantized operators that now are decomposed according to the number of substitutions that they perform. So 1, 2-body, 3-body, and so on. And each component is the difference between an operator that excites electrons and one that de-excites electrons. So here's how, for example, I would write it. It's in normal order form, and there's a set of amplitudes that parameterize the operator. So now that I have set up with the entire system formalism, what can I do with it? So I can do standard perturbation theory. So I can do second order, third order. I just have to decide a way to partition the Hamiltonian. This typically leads to methods with low costs, like n to the 4th. But I can also do non-perturbative approximations where I, say, truncate the particle rank. This is exactly what you do also in couple-cluster theory. And then one of the problems is evaluating the transformed Hamiltonian, which here we use a technique that was developed, or a proposal by Takeshi Yanai and Gardner Chan, where basically every time we compute a commutator, we keep a certain amount of the normal ordered operators, 1 and 2 body, or 0, 1 and 2 body, and so on. All right, so let's see. Okay. So I wanted to spend a lot of time discussing informalism because I think to me that was kind of the more math heavy and maybe could spark discussions. And from now on, I'm going to show you what we can do with this. Maybe if I have time, I can show you some of the more interesting things we've done recently. But for example, one of the problems or features of the theory we have is that now we have a parameter in our theory. So we have to understand how we choose the parameter. How does the parameter behave when we have such a new feature, which is not typical of many-body theories. So two strategies we can pick this value of S. So one is you can treat it as a parameter, almost like in DFT. So we can run a large number of calculations and validate and choose a parameter that minimizes kind of the statistical the error on if we do statistics on many molecules. We can try to go to nonperturbative approximations that tend to be more robust to intruders, so that we can push this transformation to larger values of S. But more importantly, I think there's a strategy to eliminate this dependence on S, is because we have operators. We're not throwing away information. We just have to account for them once we have our model, we should enlarge it a little bit to account for these intruder-causing parts of the operator that we're dealing with. But today I'm going to talk to you about only the first strategy because it's the one that is easiest to implement. So here are, for example, calculations done on a diatomic molecule. And I have, so this is hydrogen fluoride. I have near equilibrium bond distance, twice the bond distance. And what happens is as you stretch these molecules, you get a buildup of strong or static correlation. Here's how the second order, third order, and non-perturbative with 1 and 2 body operator approximation work and depend as a function of S. So 0 here is the exact solution because still we have fewer electrons. As you can see, the second order is not particularly accurate and it has a kind of a bit of a strong dependence.
Question.
Yes.
So the normal ordering depends on this reference state? And
yes.
What reference state are you?
So we start with, we pick the initial reference state comes from diagonalizing the bare Hamiltonian. Yep. But we also have developed techniques where we do this iteratively. So you start with a reference state, and then you end up getting a second state, slightly different after diagonalization of effect Hamiltonian. And you take that state to be your starting point again. So we can do that self-consistent. It shows improvements, which is a bit unfortunate, but that's the right thing to do. So the theories are generally robust until values of S equal roughly 10. And we see this happening. So what's nice to see is that the non-perturbative theory tends to be very insensitive to the choice of this parameter. After you reach a certain value of S, you kind of recovered most of the correlation, and then the non-perturbative approach picks up most of it. But it can be non-convergent, so when you pick very large values. So our pragmatic solution now is basically, we notice that this range of S equal 0.5 to 1 tends to be very accurate. And this has now been confirmed in some other studies that other people like Martin and Gordon have done, where they've taken regularized perturbation theories and they've done large data sets and found the kind of parameter that gives the best result. And that parameter is consistent with the range we're picking.
This is in which units?
So S is in atomic units. So it's in 1 over R3 squared.
Okay.
Yeah.
And your energy denominators would typically be of which size?
Oh, so they can be, it can easily be of order, say, hundreds, tens ones. Yeah, I mean, there's this, depends on the basis that we choose. But yeah. So here we are really going down to a window that it's, I would say it's rather small. So, and what we're trying to do is we try to make sure that the Hamiltonian, the effective Hamiltonian we create basically captures that low energy range. Yeah, but I would say this is definitely an aspect of the theory that we would love to find, to improve. And so discussing it with you, it's one way to try to arrive at that solution. All right, let me show you. I think we have to conclude. But let me show you the methods some way work. And one of the first things we want to see to validate the theory is to compare it, first of all, to high-level results. These actually are comparisons to experiments. And I'm showing you couple cluster theory. This is kind of a gold standard used in quantum chemistry, and these are the DSRG techniques that we have developed. So second-order perturbation theory these are errors for three quantities: the bond distance, the vibrational frequencies, unharmonic constant, and dissociation energies of these molecules. Second order, it's a little bit less accurate. Third order and non-perturbative tend to be comparable in accuracy. They tend to behave better than CCSD. This technique has partial triple excitations, which are not included in our best formalisms, but we see similar accuracy when we compare the two. I'll just end with a note on how can we, what else can we do with this? Because, and this is another interesting point about building models, is that once you embrace the fact that your model needs to have some input, that leads to the problem, what if I want to study two states? So what am I going to do? I'm going to create two different models because I have some idea for a ground state, another starting point for an excited state. I can create two effective Hamiltonian. Well, this is not a general and advisable way to go. First of all, because we can't tell if these states that we're going to produce are orthogonal or not. So they can be slightly overlapping. And this is certainly not a good way if you want to model states that interact strongly. So we have developed one extension of formalism we've done is to basically go to a multistate formalism where you now want to treat two states at a time. And we do that through basically defining an ensemble of states. So all the states that we want to represent are collected in this density matrix. And then there's a way to generalize the normal ordering to a density matrix, where now you define the normal ordering as the trace of rho and the operator equals to 0. What's nice about this formalism is that the only thing that changes practically in the equation is that you no longer have cumulants and density matrices about state A and B, but you have the cumulants of this ensemble. So for example, now we can study strongly coupled states. So this is a typical failure of time-dependent density function theory, where you consider two electronic states, you stretch a bond, and they don't do what they're supposed to do, which is something like this, where you get a conical intersection. So one point of degeneracy here, this is not the correct local, the surface doesn't have the correct properties. And techniques like the ones we've developed now can reproduce these effects. Well, so I think I'm going to stop here. Let me just it's important to me to acknowledge the people that have worked on this project. A lot of the work that I've done on the DSRG was done in collaboration with Chen-Yang Li, who was a postdoc in my group, and now he's at Beijing Normal University. Several other people have contributed to other parts of the project. We've been funded by DOE, and thank you for your attention, and look forward to your questions.